Thank you very much. Yesterday, we covered a little bit about CXL specification update for 3.1. Today, we go a little bit deeper into how to actually take advantage of it into systems. A very good place for including technologies such as CXL is Open Compute Project. That's where we basically place technologies into systems, integrate them, and eventually push them to production. So OCP provides a community to realize these kind of wonderful technologies from CXL, PCIe, JEDEC, and NVMe. Different technologies come into systems. It is good to know that CXL is organized around different work groups, board of directors, and then technical task force and marketing work groups are reporting to board of directors. And there are a number of very active technical work groups that work together, debate the use models, and eventually produce specifications. Within OCP, we also have a related project structure. Specifically, OCP Server Project includes a number of work streams and sub-projects that benefit from technologies such as CXL. For example, composable memory system, and then modular hardware system, which is mechanical and system features. Extended connectivity talks about how to interconnect multiple chassis using PCIe and CXL. So there are a number of wonderful activities within OCP that parallel activities that are happening in other consortia and work groups to eventually realize them into the systems. We have been talking about memory fabrics. CXL seems to be the right choice moving forward as a standard for low latency, high bandwidth, and open specification. The specification is in public domain now for up to 3.1. And it is a realization that working together will make it easier for people to produce good products. A little primer, if you remember, CXL is based on the type of things that you already know. You know PCIe very well in several generations. The physical layer of CXL is PCIe, but then it adds coherency protocols for memory semantic workloads that eventually produces systems with converged memory area so that accelerators and devices and host CPUs can work together on one memory region. Once we do that, then we enable ease of use for software programmers and efficient data movement that reduces energy and reduces time for executing workloads. CXL has been growing. It has doubled the bandwidth from CXL 2.0 to 3.0 using PCIe 6.0 bitrate of 64 gigabits per second, transfer per second. It has increased the connectivity through switching, the description of fabrics, and it has talked about and captured ways for us system guys to compose systems from disaggregated computing. All of these capabilities will eventually help us build shared memory regions, memory pooled regions, all within a backward compatible specification. If you start building CXL 3.0, you could have some confidence that CXL 2.0 devices will interoperate with your device. So removing the bottlenecks has been a key element for CXL. You know, for example, with PCIe, if a device through a switch wants to communicate with another device, it has to go through its host, goes up the tree and then back down the tree. That creates a choke point for the host or that CPU. With CXL, we can have a peer-to-peer interconnect between devices through switches to remove the bottleneck that was with CXL 2.0 or PCIe. With this concept, using the peer-to-peer semantics, such as a memory that enables the back invalidate channel, using unordered I/O semantics, memory devices can be accessed by compute devices, such as a GPU or an accelerator, with ease. Now, of course, we have new capabilities. Yesterday we talked about it, and this one summarizes it. CXL 3.0 enhances the support for memory pooling by adding memory sharing concept. A memory region within a memory device can be allocated and be mapped to different hosts. And once we do that, you can see that different hosts through that memory that is shared between the two can communicate. So earlier I talked about communication between devices as a peer-to-peer, device-to-device. Now with memory sharing, the hosts can also communicate through memory sharing. Now that's just 3.1, 3.0. 3.1 adds another capability I will talk in a minute. And once we have these systems and these techniques provided through CXL, then we can imagine to disaggregate compute for the sake of multiple benefits: ease of use, putting things where they belong, memory in one place, storage in one place, host and compute elements that are power hungry in a different place, and interconnect them so that you can have a different ratio of CPU core or GPU core to memory. And then CXL allows us to compose all of those using CXL Fabric Manager as a mechanism to pool it all together to build a system. Now, once we have that, then we can think of very large fabrics, and we talked about yesterday. You can have a concept of spine and leaf switches. You can have a rack. Chassis within the rack could be of different types. There can be switches, can be networking elements, memory appliance, or compute blocks. Once we do all of that, we can then increase our traffic. It's not just north and west, north and south, similar to PCIe through the tree structure. With fabrics, we can also have east-west traffic with efficiency. So composable architecture creates this concept for us, and that's very applicable for large systems such as HPC, AI/ML, or in-memory databases with large memory blocks that are shared amongst multiple nodes. You're familiar with a traditional server. It starts with a compute element and a memory that's locally attached to it, networking element and storage element. We did talk about this, summarize again. CXL allows us to interconnect another device to the CPU complex. That device could be memory device. It could allow us to have different kinds of memory. Emerging technologies can be provided. CXL allows us to have multi-ported devices, so a particular memory controller be connected to more than one server. And these are all the silicon that's available right now. People have built multi-ported memory controllers based on CXL. Now, of course, we can imagine larger systems. You can have a memory device that has multiple ports, be connected to multiple CPUs or multiple hosts, and have a large memory pool. And the memory pool can, in fact, be shared now with CXL 3.1 specification amongst multiple hosts. We can have appliance systems enabled by CXL switches. These appliances could be memory appliances, storage appliances, or GPU accelerator appliances, all connected through a similar structure using CXL memory fabric. Now, of course, we have challenges because some of these interconnects are complex, and that's why we have system people within OCP and other companies to solve some of these problems. So the way I've thought about these things is just, well, to build large systems, we need to be careful. The 3 points that I normally mention include: first, do no harm. Put things where they belong, and if it is too hard, push back and sometimes find another way to do it. So within the first principle, first do no harm, if we disaggregate a system, from a software point of view, we still need to represent the system as what they are used to, as CPU, memory, networking, and storage. And that is a major effort that's underway as part of OCP, for example. And to put things where they belong, hardware elements, if you are not very careful, you can create new fault modes, new complexes for interconnect. Choosing how to partition the system is very important for serviceability and reducing the cost associated with disaggregating compute. And that's another element that OCP is working on. And once we do all of those, we can think of a reference hardware that software people can use to develop their software. You could call that one a reference software, and it could be ready for future systems. An example of that could include a mesh of compute elements and memory and storage and switch elements that can all be in mechanical structures, plugged in using cabling techniques or PCB techniques. For that, a backbone, copper backbone, seems to be very reasonable. You have one element, serviceable element, that is it could be one part number that creates this copper backbone. Interconnect can be photonics. If the devices are farther away, within a rack, for example, or multiple racks, photonic, these are the concepts that are being discussed within OCP. So then you can imagine multiple modules, all interconnected using copper or photonic elements. And of course, for systems, we need power and cooling. And OCP rack and OCP servers are good examples of what system designers are doing. So having all of that, you can imagine have a tightly connected local compute and memory, and they can be connected through expansion chassis and disaggregation for appliances. And that looks like having an aggregation point using fat pipes and lots of interconnects within the individual tightly connected clusters. So efficiency on data movement can be handled using different techniques. For all of that, we need software. CXL Fabric Manager, an essential element to do the system composition. UFI can be used for pre-boot, and those are normal techniques that we've used for PCIe. We can expand that one across for CXL as well. So this creates multiple layers for CXL. Physical layer based on PCIe today, UCIe is another, and then we have software layers. Even if we change an element of the full multi-layer system, other layers are applicable to move to another technology. So having this technology, then it is good for us to have ways to realize them in systems, and OCP is a very good technique to do that. As I suggested earlier, within OCP server project, we have multiple work streams that are thinking about and doing work around composable memory and CXL-enabled solutions. Composable memory system, CMS, is very active. I encourage you to participate. It touches on software elements and system elements. DCMHS is mostly around hardware, modularity, and standardization on how the cables and connectors and adding cards and what we used to call motherboard, now we call processor memory modules, HPM, and how they are interconnected. So within a composable memory system work group, the teams have structured themselves around multiple work streams. And work stream is working on the workloads and defining the use cases for this. As I said earlier, once you disaggregate things, we need to have a management entity. Fabric Manager is an entity to pull it all together. And then, of course, Fabric-enabled solutions targeted for AI, ML, and HPC is a very interesting topic for a lot of people these days. There's good activity going on over there. Competition programming and working with academia are other work streams that the team is working on. They do have an extensive plan for 2024 for this year to move these concepts forward. And the work is being done in conjunction with other co-travelers, different consortia, the MTF, JEDEC, CXL, SNIA, and others to bring good capabilities into systems. The other sub-project of server project is the DCMHS. They're working on mechanical structures and standardization of how modules fit together into a system. The extended connectivity work stream is responsible for defining requirements for chassis elements. Inside the chassis and chassis-to-chassis elements, they have a specification contributed to OCP that defines the length of these cables, how well to design them, what connectors to use, what expectation they have on the distances between these racks or chassis. So on a parallel effort, there is a open accelerator infrastructure, OAI, that where it's active. It started with a definition of OAM, OCP accelerated module. Later, it created a specification for an infrastructure around that OAM, that's OAI, and they have pushed out their specifications into larger chassis, and they're very active on that aspect as well. So once you have a chassis that's defined around OAI, other people can think about how to interconnect those chassis together to make a very large structure out of them. They could be based on CXL or other potentially proprietary methods of interconnecting these chassis together. So to summarize, on the first do no harm part, software compatibility is very important. Security and management are paramount. For that, within OCP, there is composable memory system work group that is trying to create a semblance of the same server that used to be before disaggregation. So that is the effort on that side. On the put things where they belong, modular hardware system team is working on very good, feasible, correct partitioning of the systems and standardization on the interconnect. So once people are done with their designs, devices can be interoperable. And on the pushing the envelope as far as big as we can go, the extended connectivity work stream within OCP is very active on that. Push it as far as it goes, but then if it is too hard, find another way. You start with PCBs, then interconnect them within a chassis, and then sometimes interconnect chassis together, and sometimes you use copper, and sometimes you use photonics. So when you put them all together, then we will have systems that can realize technologies for memory fabrics based on, for example, CXL. So that is the way that CXL technology can find itself into systems, and OCP is a method that we can realize these into products. I will close on that, Frank.